So let's try this out. First of all, get that off so it won't make you dizzy. Let me, oh, it is? It's not sure. There it is. In here for a few seconds. Well, you have to get in here. So actually, I put all the due dates and everything is out there now. Section 2. Not that there's any difference between us, but if you go out there, okay. Okay, so all this stuff is here. I don't know. You probably know how to do this better than I do. It seems like most places should have a calendar with across it. I didn't find that. I don't know how to do it, but I did find. Now it doesn't show anything in the future, but that's because mode. Give me a second. Over again. The only calendar I could find, or the only way I could find things listed in the calendar, maybe you know how to do it, that said the future. And then the due date on everything. But I couldn't find a calendar. I mean, you can do this week. Is there a way to look at an entire calendar in this thing, or is there not? Really? Okay. There you go. So it wasn't just me. I don't know. A calendar with it all listed on it, but I don't know. So let's go into here. Let's see. Statics. One of these is, oh gosh, I opened too many. That's it. Cannot open this file. Well, I don't know why you can't open that file. Okay. I guess I'm going to have to shut it down and go find the thing. That's new and different. Okay. Let me see. Now I'm off looking for, good grief. Let's see. That's not where I had it, but maybe that's why I couldn't open it. I don't know. So Oh, it goes up and down. Okay. So we sort of poked our way through this thing. So let's go ahead and do 12, 2, 3, and 4. So if you look at this thing, here, get to 12. Well, we can buzz through this real quick. Kinematics, the only thing he's talking about when he talks about kinematics is velocities and accelerations, well, I guess, in the positions. When he's talking about kinetics, which you'll see that title, that's the F is equal to ma, or torque is equal to. So you got to do the kinematics before you do the other part. Let's see, does this work? No. Oh, yeah, it does. So I guess he's talking about some history of some stuff. And then he starts talking about, which he decides to use S as the position, which there's nothing wrong with that. I mean, somebody's got to use a symbol somehow. So he goes through here, and then he takes the derivative to get the velocity. Now, there's some tricky problems in this section, and I'm not sure if I assigned it, but I'll talk about one of them in a second. He starts talking about the average, what's the average speed, and that can be tricky as well. And so as far as some of the problems in the way he states them, he goes through the accelerations. You've seen it before, nothing fancy. He does this, which is a little strange. And at first glance, let's see, this is dynamic. So the question I'm going to have to figure out is whether I need to have 2 sessions for here, or should I just lay them out here? For right now, I'm just going to lay them out there, and then the way you'll see it is your time will tell you. If you look at that top left corner, you'll see the date and the time. So if you're in the 11th section, anything from 11 to 12 that got created is your lecture. Anything from 2 to 3? No, wait. 1 to 2. 2 to 3 is the other one. So the way how this worked, and I'll give you some idea of why you'd want to do this. So he has this is equal to acceleration. That's you've seen that before. There's nothing fancy about it, but this kind of implies you've got to have this, is equal, I'm going to make something up, t squared. So if you've got that, everything is great. But let's say you were sitting on there and you had sitting on a car, an object or something like that, and for some particular reason, you had the velocity as a function of position, say 5s. Let's make it s squared or something like that. So in other words, you were in the car, and whenever you look right here, there's a certain speed. I'm assuming if my s is going to the right. When you're over here, it's faster, and so on and so forth. So when would you ever do this as opposed to this? And there's a simple case, and it's called a wind tunnel. It sits over in the bottom of Corley on this end of the building. If you sit there and look at that thing, okay, halfway decent picture of one. A big glass section, not glass, but plexiglass right here. It's got a big fan here, and it pulls air through. And what you do is you stand right here, and you stare at something. So you're staring at it. You're constantly staring at it. You look at it, you see it. The velocity is a function of position. Now, take that to another step, and let's say, let me zoom in on this and try to make it look a little bit better. Let's say somebody was staring at this spot right here. He stared at it over and over and over, and he said, oh, it's going 5 miles an hour or feet per second or something like that. So you sit there and you stare at it. The longer you stare at it, you realize, oh, it's not changing velocity. Is it accelerating? Okay, now let's think about this. You look back here, and then you look up here. What do you think the speed is right here? They haven't had, well, now wait a minute. I heard somebody saying they were in thermo, right? So y'all are in thermo. Have y'all done mass flow rate stuff yet?
No, we actually are stuck on a problem with you.
Yeah. Well, let's put it like this, and you've probably experienced this. So, if you're standing, okay, how do I explain this without any equations? If you're shoving, okay, it's air, water, whatever. If you're shoving this much down here, so here's a big slug. That's a water balloon. It's a square water balloon, mind you. And then what happens is it goes down here. This water balloon has to fill the same spot, right? So what do you think it looks like down here? Does it look like that? Or does it look like this? Which one do you think it looks like? You think it looks like that? So in essence, since it was a water balloon, I'm assuming now it's a water tunnel instead of a. What you're saying is you're saying it squished all that water down. And what actually ends up happening is this velocity, I'll just call it high. And this one, I'll call it low. And so what you'll learn in thermo is you'll end up with the m dot is equal to the density. Have y'all talked about density yet? Okay, density. The area, which is the area that this person would stand and see, and then the velocity, which means that if it's going slow here, when it shrinks down into a small area there, it's speeding up like crazy. Does that kind of make sense to you that would occur? Okay, so then if I'm seeing that, I can argue that, say, maybe this is 10 feet per second or miles per hour. It doesn't matter what the units are. And then a person standing here, so there are three of us standing there. One person sits there and writes 5 over and over and over. His neighbor sits there and writes 10 over and over and over. And this person say, I don't know, how about 2? You know what? I want to make things easy for me to calculate. So I'm going to say that's 7. I just wanted the difference. Wait. Can I rechange that? 8. That way, the difference between me and my neighbor's 3, me and my other neighbor's 3, right? So I just did that for convenience. So the key is if I'm the particle, I'm tracking myself. And from here to here, I speed up. From here to here, I speed up. And then from here to here, I don't care. So in fact, during this part, it is accelerating, but you stare at it and it's not accelerating in your mind until you realize the equation is different. So let's take a look at the equation for a minute. Does that sort of make sense? It actually is accelerating, even though you stare at a spot and it looks like it's not changing its velocity. So let me tell you why that's the case. So if you look at it, you no longer have velocity as a function of time, but you do have it as a function of position. You can take this derivative. I think I had 5s squared. Okay. So I have velocity is equal to 5s squared. It could be anything, but it's just a function of position. And then what happens is I've got to get back the same thing. So this is that chain rule that I'm stuck with. So if I'm stuck with that, this one I can figure out from this equation. This one just becomes the velocity. So if you look at it, they usually write it like this. I could write this as something else, but let me do it like this. You start thinking about it, well, let's just look at this case back here where I'll make it more. So here is, what was it, 2, then 5, and then 8. Then let's say the delta S, the distance here between these is both equal. And just for the sake of argument, it's just equal to 1 because I can divide by 1 pretty easy. So if you look at this and you're this person staring right here, you would write 5 times the change in velocity as a function of position. So in other words, maybe I should have done this like this. 2, this is 5, and this is 8. I conveniently tried to make it a straight line. So in fact, this is change in velocity with respect to position. As you move, as you focus your eyes on some spot of the wind tunnel and then you move your eyes over, it's different. If it's different, then it accelerated because, just because of this. So in this particular case, 8, end up with 3/1, or the acceleration in this case is 15. Does this sort of make sense philosophically as to why this is? I mean, you've probably seen this too. You look at a puddle or look at a river, and as the river comes down, you can sit there and watch it. But as if you haven't gone to Long Pool, and you're back in that area so if you're sitting there, you're looking at it, it's the pool, it's over to the right. There's a big it's like a big lake. There's not much happening there. You sit in your canoe, you're not doing anything, and you're like, wow, I'm waiting for it to get to the rapids. Well, that's what happens. Here's Long Pool. Okay, so it depends on the way, if you're looking from right to left. Here's the big part. Here's that big rock you can jump off of. But don't hit your head on the bottom. And then it goes down like this. Well, when it's going down here, it's rapids. Back here, it's barely moving. So this is the concept. So what you're doing is, the particles of water, they did accelerate. They're moving along, and then all of a sudden they're going real fast. But if you stare at it, and long enough, you sit there and stare at that one spot, it looks like it's going the same speed. So that's what he's doing here. Where'd the book go? He's talking about this. Now, what I've done is I put them together, but you can just as easily take those things and separate them apart. Meaning, well, sometimes it just dies on you. Acceleration, ds is equal to v. Now, depends on what you have represented as what. So if he gives you the acceleration as a function of position, you can put it in here and integrate it and take off and solve that. Of course, what you have here is velocity at position 1, and then this is position 1. You always have to realize these are bound together, upper and lower limits. S2, velocity at position 2. So this is bound here. So if he gave you, I don't know, acceleration is 3s, for example, you could stick it in here and integrate it. And that's what he's setting you up for right here. But of course, he doesn't do it for a while, does he? Well, okay. So he starts in on doing it here. He starts considering constant acceleration. Now, what you're not supposed to know yet, you're just supposed to accept that there's a lot of cases that have constant acceleration. But there's a good reason they do, is because you have a constant force. If you don't change your mass, like you're moving down the road throwing stuff out of your car, and you have a constant force, then you're going to have a constant acceleration. So there's a lot of occurrences of that. So he basically hones in on that. Plus, the parabolic motion or projectile motion, whatever you want to call it, that actually has constant acceleration too. So you go in here and do this. You've seen these equations. Nothing's new. There's the weird one. So the weird one is, okay, on the left-hand side, you got V naught, S naught. These are the parts that are tied together. These are tied together. And then if this is constant, you just pull it out and you stick right there. And then you just have, the reason you have 2 stuck here is you had a half on the other side. This is V squared over 2, integrated from V0 to what? V? And then he does this part, I guess, is that part. V, and then the V0. He took the V0 and shoved it to the right-hand side. That's all he's doing. So if you look at that there, that's a case right there for if you had a constant acceleration. Now, in the wind tunnel, I don't think you could argue that this because there are different particles around and different things can happen. But if you're looking at a car or something like that, or a projectile or something, that may be the case. So that's all he's doing, is he's just doing that. There's nothing fancy there except just a new equation that you probably, I mean, you probably are. Did y'all mess with that one at all? And when it came to, that's the only thing that's added here. And, you know, not to confuse the issue, but you'll face it later on. I mean, and it's not that important. But the difference here is, okay, it's not paying attention. Okay. The difference here is if you stare at something like this, they call it Eulerian frame of reference. But if you decide to follow it, you know, jump on it and take it for a ride, they'll call it Lagrangian. And if you're in physics, if you want getting a physics major, they really, I mean, they beat that into you really hard. And rightfully so. I mean, those are two different frameworks and two different ways of looking at things. It doesn't change the fact that if a particle is accelerating, it's accelerating. There's nothing more about it. So then he heads off, I think. Oh, then he says, I'm done. Procedures for analysis, coordinate system, kinematic equations. And then it's just, it's kind of a free-for-all then, but everything is, the free-for-all is, what is he going to, he's going to make up stuff and give you problems. So here's your free-for-all. He says this, okay? And then he gives you the times, and then it's up to you to carry out the integration or take, you know, do something like that. This is the stuff that would be okay in a homework, but I'm not going to do that on the test because I don't want to have your calculators compete with each other. You said you had 4 calculators or 3. So, I mean, she was carrying what, 20 calculators out a minute ago? So, I mean, there's so many calculators that I'm kind of embarrassed to say I have no calculators. I just use MATLAB for everything. So, I just don't want to learn another calculator. And it's just, you know, it's like every time they come out, there's something new on them. Use MATLAB. So, I mean, the same problem gets happened over and over. Here you got, so here's a key. If you're sitting here looking at that, he's got this sort of tied up into where its acceleration is a function of the velocity. So he's done this, and then the acceleration gets removed from it because you have velocity right here, and then you have this. So you have to slide this underneath there and take the dt over to the side. So that's exactly what he does. This is one of those ones that's completely odd, completely offbeat, but it does, I mean, his first thing is setting up, he's using the equation, basically this basic equation. Often, if you get confused, you can just write one of those down and try to write what was given to you. And then think about it for a few minutes and it works its way out. So, that's granted, that's a very strange one. But he's an expert at giving you strange ones. Okay, here's one typical example. This is another thing he'll trick you on in the homework. I'm not going to do this to you on a test or anything, but here he'll say, okay, travels upward, determine the maximum height. Da, da, da. Okay, now he doesn't ask the question. A lot of times he'll say, okay, what is the distance it traveled? So often you'll look at it and you'll say, well, let me give you a case, just a hand waving kind of case. Okay, that's what I have to do, I guess. So in a hand waving case, let's say you had something like this. Position is something like, okay, and this I got to think about. Say it's a third order. I said third order, and I did 2. Squared plus t plus 5 or something. So let's say this thing went out here, went to here, came back to here, and then ended up like this. So there, you have to sort of track this. So what I'm saying is, let's say this is time and this is position. So obviously say he starts here. So let's say the equation does something like this. Now, at first glance, you would say, oh, the distance I traveled was, say, 10 here. But in fact, that's not true, because the total distance you traveled that far, then you traveled back to here, then you traveled up to here, and then you traveled all the way down to here. Does that make sense? He tricks you on these homeworks that way. He'll ask you, and you'll get the answer, and you'll just plug in S at t is equal to 50, and then you'll plug in S at t equals 0, and you'll say, well, I'll subtract those two, and that's the distance I traveled. Well, no, not necessarily. I mean, think about it like this. I got to go to Little Rock Tuesday. So I get in the car, I leave my house, I went to Little Rock, I came all the way back. I'm at the same place I started from, so the distance from where I was in the morning to that afternoon was 0. But the distance I traveled was what, 120 miles? I went all the way to Little Rock, and I went all the way back. So he'll trick you in this, and it's a little confusing if you're trying to answer these questions back that way. So, and I hope I assigned one now. Said all that, and I hope I did, but if I didn't, I'll do something about it, I guess, somehow. I don't know. So all these are the same. They basically a set of problems, and there you go. So let's go on to, I don't know, do we want to find one that has a distance travel? That's fine. Oh, wait. No, that's not distance. I would search for the word distance, but I can't. I don't think I can on this document. Okay. Ooh, wait. And the distance traveled. But this is not a good one, because it's a constant acceleration. That's no fun. What distance does the car travel during this time? I want something more complicated. Oh, wait a minute. Here you go. Hint, plot the path to determine the total. All right, so here's an obnoxious one. We'll just do it, whatever. I mean, we got to do something here. I mean, that's what you paid for, right? You did pay, didn't you? If you didn't, that's all right too. I'm not the bill collector. Okay, so let's do this one. And of course, just to show you, I don't like using anything but MATLAB anyway. So here, the position of the particle along the straight line is given by all that stuff, where t is in seconds. Determine the position of the particle. Oh, that's okay. And the total distance. Okay, well, this is okay. We'll do it anyway. We started down this path. So here we go. I like MATLAB. You might like your calculator, but that's okay. We can meet in the middle. Okay, so that's why MS, that makes that thing symbolic. So if I wanted to, I can say S is equal to 1.5 times P to the third minus 13.5 times T squared plus 22.5 times T. Oop, did I end it? Yeah, so it gives you that equation. Not anything fancy, but I think there's a thing. Easy plot. It's not spelled out. Like that. Let's just try it that way first. Okay, but now what you've already see is that EasyPlot decided that he wanted a different limit. So I think 0 to 6 seconds? Was that what he said? Oop. Okay. So here's what the thing does. He said 6 seconds, right? Yes, 6 seconds. So at the end of the 6 seconds, it looks like I'm at, I don't know, you can hit this button, and I think you can or you can zoom in. Here, let's just zoom in first. So it looks like we're around, it's 6 seconds, looks like around 27. So, I'm sorry, minus 27. That's all great. But what we've actually done here, might as well, we have, I wonder how I can do this. I bet you I can do it this way. I'll embed, come on, where are you going? There we go. I'll embed this plot. Yeah. Come on. Hello. Hello, hello, hello. Hello. Y'all know what that's from, don't you? You don't watch any Three Stooges? So we went this far. Then we turned around and went that far. Then we turned around and went back to here. This one I think is pretty easy. Really, y'all don't watch any Three Stooges?
I've seen the movie.
Oh, yeah? Okay. This, I think, is 10. This, I'm not sure. I'm not sure where that is. However, if you just want to kind of be approximate, I can pretty much grab, looks like minus 37.5. So I think this point's minus 37.5. And what did we decide that one was?
Negative 27.
Minus 27, okay. So it looks like this distance, I think that's about 10. And this would be 47.5. And then, what is that? That's 10, no, 9.5, right? Is that 9.5? No, 10.5. 10.5. So 10.5, 47.5, and 10, that's the total distance it moved. So, and as far as I have recollection of, maybe I assigned that one. So if I did, then I don't remember if I did or didn't. I was just sitting around all Saturday doing all the assignments and everything. So that's the only thing that really catches you off guard. It's the only thing I've ever seen people get caught on in that section. And it's not anything that big. So if we do that, move on to erratic motion. Oh, okay. So he calls it rectilinear erratic motion, but I guess for that matter, it really doesn't matter. All it is a plot, and essentially your slope, if you're with position and time, the slope is the velocity. If this is velocity and that's time, like that, then the slope is nothing more than the acceleration. That's all it is. So generally in these cases, oh, and then, okay, is it the next page? Yeah, it's the next page. The next thing is, if you're moving this direction, in that, instead of moving, here, let me do it this way. So take velocity, for example. If you're doing this, that's great. If you're doing this, though, and you have velocity as a function of time, then you've got to do an interval. So you've got to do ds is equal to v dt, and you've got to say t0 to t1, s at t0, s at t1. And you've got to integrate this in order to get the position. So what happens to you, it seems weird, but let's say you have this. So if you want to know the position right here, you take the area to the left of you. And then if you want to know it right here, you take the area to the left of you. And so obviously the area continues to build up. So you're building up unless you do this. So you do something crazy like go rapidly that way. And say now you're looking for the position here. Well, here you have all this positive area, Now you got some negative area. What's happening when you're gathering that negative area? You move the position, and then suddenly you're starting to decline. Now that doesn't mean if you build up so that this area here is equal to that, you'll end up at a zero position. And then if you keep building up negative area, you're going backwards. So it's kind of like, think of it like this. I'm driving this way, the velocity. I slam the thing in reverse. Eventually, I'm going to cross the location I started from, and then I'm going to be going backwards for a while. So it's all basically the integration here. Now, most of the time, the cases he give, here, we'll get into, okay, and you have this one as well, but generally I don't focus that much on it, but it's still integration. It's just that you have a velocity squared there, so it's a little bit obnoxious because you got to remove the initial velocity over and take the square root of something. But here, let's get down to a case in point. What does he have? Position and time. Well, there's not much you can do here, because if you've got position and you've got time, only thing you can do is take the derivative and get the velocity. So all you're doing is taking the slope here. Slope here is the same. So speed's 20 from there out. Speed starts out here, ends up hopefully at 20. This is the problem in constructing these graphs, is if you're making a test, and I've noticed this before, at this point, you would like to have, it would be nice to have the slope on this curve to match the slope on that curve. However, you can make a mistake and have a jump in the curve. So if you look at it, that's exactly what you have. You have the 20. You can take the differential if you want, and you'll end up with 2t. So you get this plot straight up like that, gives you that. And then the boring part is the boring part now is if you take the slope of this, you get just a 2, which is pretty boring, and then it dies off and it becomes 0. So, there's nothing fancy about it. It's just a bunch of, here's an acceleration. Well, if you have an acceleration in time, the only thing I can do is go backwards. If I'm starting up here at acceleration, go back to velocity, I've got to integrate it out. So if I want to know the area A1, I guess that's 10 right here, and this is 10, so that's 100. Velocity at 10 should be 100. Okay, well, velocity, yeah, if I put in time of 10, I get 10 times 10 or 100. So now if I want to know the velocity right out here, well, I don't know what he's saying out here. He's saying determine the time needed to stop the car. Okay, so what he's doing with this is he's putting on the gas and accelerating like crazy, and he wants to know how far it is before he stops dead. Well, that means this area has to cancel that one. Well, here, this one's 100. This one goes down 2 times something. It's got to equal minus 100, or basically it's 50. Yeah, minus 50. So essentially, this distance from here to here, distance being on the plot, which is time, that has to be 50 seconds. I'm assuming since that's 10, the total is 60 seconds. So it took him 60 seconds to stop the thing. From dead stop, accelerating, and then dead stop again. So he's counting, if you're counting this 10 seconds right here. Oh, and then he plots this thing. And not too surprising, here's your slope, and there's your slope, that's the -2. So, it doesn't take you long to figure out you can do these fairly easily. And it just gets like a constant repetition, and pretty soon you're kind of annoyed by it. It's a whole bunch of them. Then, of course, he does things like this. He entertains you with different pictures and stuff. That's actually what you're paying mostly of this book for, is the pictures. Because when I took it years and years ago, they didn't have as many pictures. And I think I paid like $12 for the book or something like that. So obviously the difference is the pictures. Oh, and the color. the ink in there, the color ink. But as you can well see, that's color, but that's not ink. So it just, maybe that's, I don't know. So what I'll do on the test, I can guarantee you that I will give you one with a velocity and a time and make you integrate and go one way, and differentiate and go the other. Now, I'm not going to make you do the picture like he did. What I'll probably do is sweep in here and say something like, how far did it go in t is equal to, how about 40? In 40 seconds, how far did it go? So at first glance, you're thinking, okay, wait a minute. If I take a differential or slope of these lines, that's the acceleration. So in 40 seconds, roughly, that's a straight vertical line. This area right here, 12 times 30 over 2, because it's a triangle. Yeah, and then I got to get, yeah. So then this part of the rectangle, yeah, 10 times 12. Add those two up. I was trying to think of what's 10. 6 times 30, is that 180? So 180. I think this is 120. So if I add 180, 120, what's that, 300? And I don't know whether this is feet or something. It doesn't really matter. Oh, sorry, meters. Did I do that right? If I didn't, you're supposed to stop me. Is it?
Yep.
Getting close. So, I mean, this erratic motion stuff, it's just erratic and stuff, but it's not really, I mean, I don't know why they title it this, but here, you go through them, you keep looking at them. Okay, then the next thing is curvilinear motion. The only thing that's different is he has this as a vector. The vector could be represented in different coordinate systems. However, what he lays down here for, okay, well, okay, he does it right here. He lays it down in XYZ coordinates where I, J, and K are your base vectors, something you've seen before. Y'all have seen that before, right? I, J, and K and all that. And then basically, when you're looking at these now, you have to look at them like X is a function of time, Y is a function of time, and Z is a function of time. And that's the only difference. Before, it was S as a function of time, and it was all by itself. Well, these are actually independent. So the X is independent of the Y, which is independent of the Z. So you're just doing possibly three different problems, just like what the one was like. So if you want to know, I want to know the acceleration in X, it's the change in the velocity of X. And then if I want to know, if I want to know the velocity in X, it's just change in X with respect to time. That's it. That's all there is to it. It's just that usually you want to indicate a subscript there associated with the coordinate direction, dimension coordinate you're using. So are you guys starving? Really? Wow. So do y'all go right over there?
No, I don't know.
Or Quiznos, huh? Well, let's see. Next time we'll head off. I mean, this is kind of a repeat. This sets you up. There's a bunch of X, Y, Z's, and it's setting you up for this. This is what the next part is. So we'll come back in and start in on projectile stuff. And that one I'll spend some time. You know, I've been sort of lax here for the last few minutes. But this one I'll spend some time plucking a few problems out and working them. Because those are on the erratic thing, and those are on the homework assignment. So I guess we got to go. No? Oh, yeah. Okay. Thank you.
Thank you.
Thank you.
I just want to be